Right, I'm going to go over some triple physics higher paper 2 questions. SP8 Energy Forces doing work unit and the SP9 Forces and their effects unit. So these are all past paper questions from the most recent physics papers with grades 9 to 1. Question 1. Figure 8 shows a bicycle. The rider uses the pedals to make the large gear wheel turn. There's the large gear wheel on the front. The large gear wheel moves the chain. The chain turns the small gear wheel. The large gear wheel has 48 teeth. The small gear wheel has 12 teeth. The large gear wheel turns 2 times each second. Calculate the number of times that the small gear wheel turns each second. So if you've got 48 teeth on that large gear wheel and 12 on the small, each gear wheel is still going to turn 1 tooth for 1 tooth. So for every full rotation of this large cog, 48 teeth are going to turn, which means that 48 teeth are going to turn on the small cog. So if the large cog turns once, the small cog is going to turn 4 times. In this question, it says that the large gear wheel turns twice, which means that the small cog will turn 8 times. Another way of doing that is by saying 48 teeth divided by 12 teeth equals 4 turns. So because the small gear is 4 times smaller than the large gear, for every 1 revolution of the large gear, the small gear has to turn 4 times. So if the large gear turns twice, the small gear is going to turn 8 times. Oil is applied to the wheel of a bicycle at the point shown in figure 9, right there in the axle. Explain how the oil improves the efficiency of the bicycle. Let's start with the simple answers first. The oil is going to reduce friction. You might get 1 mark for saying that. If you're going to reduce friction, you're going to reduce the amount of thermal energy transferred. So you're not going to waste your kinetic energy as heat energy. Now that basically means that more of the energy that you use to pedal, instead of getting turned into heat energy, it's going to actually stay as kinetic energy, which is what you want. And the last way that I answer these type of questions is by using the equation for efficiency. Efficiency equals useful energy out divided by the total energy in. So what that means is you can still put the same amount of energy in, but you're going to get more useful energy out, and that will increase the efficiency. I would definitely mention about the efficiency equation. Examiners like to see that. Figure 12 shows 3 toy animals hanging from a rod. The rod hangs from the ceiling by a string tied to the centre of the rod. The system is in equilibrium. So that means it's balanced. Use the principle of moments to calculate the mass of the toy elephant. Right, it's very important that you pick up on the fact that it's in equilibrium. If it's in equilibrium, the first thing you want to say is that the clockwise moments equals the anti-clockwise moments. You'll get 1 mark straight away for saying that. If you can't remember what a moment is, moment equals force times by distance. Or really you should say a perpendicular distance from the pivot. So in this case here, that's where the pivot is. The pivot is the point around which everything turns. Right, let's get back to this then. A clockwise moment is anything that makes something turn clockwise. So what you've got here, you've got the mass of this object here. That's what we're trying to find. Now, because the force that's involved is the weight of these objects, and weight equals mass times by gravity, since the gravity is the same for all of these objects, we could just say that the moment equals the mass times by the perpendicular distance from the pivot. Really, to make this easier, the examiner should have just had weight is 6 newtons, something like that. This weight would be 4.6 newtons, and this weight would be, well, whatever, we're trying to find it out, aren't we? So if we have the weight of this object here, it's pushing down. Now follow the direction of the force and go round the back of the pivot and keep going in that direction. And what is that direction? It's clockwise. So this elephant is providing a clockwise moment. So if we say the mass of the elephant times by the perpendicular distance, that is the only clockwise moment that we've got in the picture. And that's going to equal the anti-clockwise moment. So if we look at this duck, the duck's force would be coming down, that's the weight, go round the back of the pivot, keep going in that direction. What is that? That's anti-clockwise. So you've got the mass of the duck, which was 4.6 grams, multiplied by 10 centimetres. And we need to add that to the moment of the rabbit. So the force is going down, go around the back of the pivot. Yep, that's going anti-clockwise as well. Now you know just to leave things in grams because they want the mass in grams. So that equals 4.6 times by 10 is 46. And we'll add that to 6 times by 15, which is 90. So that's 136. And that's going to equal m times by 17. So if we rearrange that, m is going to equal 136 divided by 17, which equals 8 grams. Now if you wanted to double check that the units were correct, if I'm multiplying grams by centimetres, that would be 46 grams centimetres. That's grams times by centimetres, so that would be grams centimetres, which means that this here would be grams centimetres. So grams centimetres. And this 17 was centimetres. So if you're dividing grams centimetres by centimetres, the centimetres is going to cancel out and it's just going to leave the grams. So that's definitely correct. I would rather have saw these masses given as weights. That's really how it should be, because the moment is force times by perpendicular distance, not mass times by perpendicular distance. I don't know if they've done that on purpose or what, but it doesn't matter. We've got the right answer. Question 3. Figure 7 shows a person trying to lift a large rock using a metal bar. The rock weighs 1,800 newtons. The person can only produce a downward force of 600 newtons. So that's their maximum force. The person cannot lift the rock. Explain using calculations why the person cannot lift the rock. So using calculations. Well, we've just said in the question before, a turning effect, which is what we need to lift the rock, is called a moment. And the moment equals the force times by the perpendicular distance of the force from the pivot. If you wonder what perpendicular means, it means at 90 degrees. So what you've got is this distance here from the pivot. That force is acting straight down like that. So the distance we needs to cut across that force at 90 degrees. If they tried to be crafty and they said that the length from there to there was 0.3 meters, ignore it, because that distance there does not form a 90-degree angle with that force. They usually don't try to pull a stunt like that anymore though, but you never know. Right, so you'll probably get 1 mark for saying moment equals force times by distance. Now, let's have a little look at the moment she's producing. If the pivot's there, she's pushing down this way. Right, just like the last question. Follow the force and then go round the back of the pivot and then keep on following the force. Is that going clockwise or anti-clockwise? Well, it's anti-clockwise. So her anti-clockwise moment equals her force, which is 600 newtons, times by her perpendicular distance, which is 0.5 meters. So that's going to equal 300 Newton meters. Now the rock's moment, follow the rock's force going down, go around the back of the pivot. Right, that's going clockwise. So the rock's clockwise moment must be bigger than 300. Let's work it out. 1800 newtons times by 0.2 meters is 360 Newton meters. So basically, the person's anti-clockwise moment is not big enough to move the rock, because that's creating a clockwise moment of 360 Newton meters. Okay. Explain one change to the arrangement that will make it possible for this person to lift the rock. For this person. So not another person, not extra people. And the arrangement. So sometimes people, and sometimes this is accepted as an answer and sometimes it's not. Sometimes people start to say, well, use a longer lever, and they start to say get an extra person to push down. I don't personally like to say that. I don't like to change anything. It is what it is. Go off what they've gave you. Now you can see from the picture that the lever, she's not quite pushing on the end, is she? So if she was to push on the end, then this distance would be longer. And if that distance was longer, she'd have a bigger moment. Okay, the moment equals the force times by the perpendicular distance. It's said, now this is why I'm coming back to this, that the 600 newtons was her maximum force. So you can't just say increase her force to increase the moment, which it would, but she's already pushing as hard as she can. So the only thing we can do is to ask her to increase the distance that she's pushing. So in other words, get it to push from the end, it'll increase the perpendicular distance and that'll increase the moment. And then hopefully her moment will be bigger than the rock's moment. And that should get you the 2 marks. Question 4. Figure 6 shows 4 forces P, Q, R and S acting on a rod. The rod can rotate around an axle. So there's the axle. Which force will make the rod rotate about the axle? Right, well if I push at P, it's just going to try to push against the axle. Well, that's not going to make it turn because the axle is like a big bolt that's connected to something. If I push at Q, yep, that'll make it turn. So I'd imagine that's the answer. Let's just double check first. If I push at R, well, there's no point pushing at R because you're pushing on the axle. And if I sort of pull down at S, that's also right at the axle. That's not going to do anything. So the answer is definitely Q, and Q is the answer B. Question 5. Figure 10 shows an arrangement of gears. Each gear turns around a fixed axle. So the same thing. Axle would be in the middle. Gear P is turned through 1 complete revolution per second. So there's gear B. Which of the following describes the motion of gear R? Right, so there's gear R. Now let's have a look at the responses first. So they want to know the speed, so revolutions per second, either 4 or 1. And they want to know the direction of the rotation of R. Will it be the same as P, or will it be the opposite of P? Right, let's have a look then. Well, P's got 10 teeth and R's got 10 teeth. Doesn't matter how many teeth Q's got. Now remember, like I said in the very first question, these teeth interlock and they're going to move one for one. Every time one of these teeth moves round, one of these teeth's going to move round. So if this spins completely round, now it doesn't say whether P spins clockwise or anti-clockwise, so you just make it up. They're only interested whether R's go in the same direction as P or not. So I'm just going to say that P is going to spin clockwise. Now if I spin this fully once, 10 teeth are going to spin round. Now if this goes down, that means that this is also going to go down, right, by 10 teeth. Now if that goes that way, it's going to come up this way, and if this comes up this way, it's going to make this cog R go that way. Okay, so P is spinning clockwise, Q is spinning anti-clockwise, and R is spinning clockwise. We're not really bothered what Q's doing, we're only interested in R. Now because they've got the same number of teeth, if this spins round 10 teeth, which is 1 full revolution, that's going to spin 10 teeth, which will only be a quarter of a revolution because it's got 40 teeth. But this is going to spin 10 teeth, which is a full revolution. So 1 revolution, and that's going clockwise and that's going clockwise. So it has to be 1 revolution and it's going the same as P. So the answer is B. Figure 11 shows the same arrangement with gear R replaced by a rack. The rack can move up or down when the gears turn. The teeth on the rack are 2 millimeters apart. What that means is that these teeth here from one tooth to another tooth is 2 millimeters. From one tooth to another tooth is 2 millimeters. Calculate how far the rack moves when P turns through to 1 complete revolution. Right, well if P does 1 complete revolution, that's going to be 10 teeth that turn. Remember, the teeth turn a 1-to-1 ratio. So for every time that this tooth turns, you have to have one of those tooth turns because they're interlocking. And if this turns 10 teeth, it means that this is going to move 10 teeth. Now, each tooth is 2 millimeters. So it's going to be 2 millimeters per tooth times by 10 teeth equals 20 millimeters. And there you go. That's how to take care of business. Now, the fact that this SP8 and SP9 is only worth 18 marks, these questions have been taken from the last few past papers. So you can see that the content from SP8 and 9 doesn't really get asked that often. In the book, I think SP8 and 9 is only worth about 3 lessons worth of content. Once we do the SP10 questions, there's going to be loads of them because the unit SP10 is massive. Loads of lessons. The harder you work, the better your grade gets. There's lots more of these papers coming up, so I'll see you in the next video. Work hard, be nice, and bye for now.